Welcome back to linear algebra. In this video, we're going to be looking at general linear transformations. As we've seen previously, a linear transformation is a function that maps from one vector space to another that preserves linear combinations. We've worked extensively with linear transformations on Euclidean vectors and have discussed that linear transformations can be extended to more abstract vector spaces. Here, I'm going to start looking at some of the properties of linear transformations and inverse linear transformations so that we can set up some powerful tools that we can use to work with them later on in the course. Without further ado, let me get my head out of the way and let's dive in. So just a review to start. If we have two vector spaces V and W, and we have a function t mapping from V to W, we say that t is a linear transformation if and only if for any V1 and V2, that's not a 2, come on. For any V1 and V2 in vector space V, and C1 and C2 in the real numbers, the transformation of C1 V1 plus C2 V2 is equal to C1 times the transformation of V1 plus C2 times the transformation of V2. And one more bit of vocabulary. If V and W happen to be the same vector space, we call T a linear operator. Right, so a linear operator is still a linear transformation, and sometimes we will still use linear transformation. But that's something that you are likely to encounter in other courses that you take. Another thing that we've worked with previously, if we assume that an operator T from V to W is a linear transformation, and we have a set B composed of vectors U1, U2 through to UN, which serves as a basis for vector space V. Then T is fully determined by its action on the vectors in B. Again, this is something we've used before, but just for a quick review, I can call this a theorem and I can prove it by picking any vector in my vector space. And the definition of a basis says that there exists a bunch of constants so that we can write V uniquely as C1U1 plus C2U2 plus ... plus CNUN. Then, if I take my transformation T on V, that is by substitution T of C1U1 plus C2U2 plus all the way down to CNUN. And since T is a linear transformation, I can split this up and get C1 times T of U1 plus C2 times T of U2 plus all the way down to Cn times T of UN. And because this is what we were talking about, determined by its action on the vectors in B. If we can define T of U1, U2, U3, all the way down to UN, then because we can represent any other vector in the vector space by a linear combination of those basis vectors, we can use that linear combination to calculate the value of T on that vector. And when we've worked with, sorry about that, when we've worked with linear transformations in the past, we've worked with situations where the transformation takes us to the same or at least a similar vector space. We spent a lot of time on geometric transformations, which mapped from R2 to R2, from R3 to R3, or from R3 to R2. We looked a little bit at transformations on polynomials, which mapped from one polynomial space to another polynomial space. So for this example, I want to define a linear transformation T, that's backwards, from P3 to R2. So if I get a polynomial, cubic polynomial, degree 3 polynomial, and I call it f of x, I am going to evaluate f at 1 and evaluate f at 2 and make those the components of my vector space. And so I want to ask the question, is this a linear transformation? To show that something is or is not a linear transformation, I'm going to call it a proof. Spoilers, this will be a linear transformation. But to show something is or is not a linear transformation, you want to take two vectors. In this case, we're looking at two functions. Call them f and g, put them in P3. And let's get two constants, call them a and b, put them in the real numbers. And then we want to evaluate T of the linear combination, a times f of x plus b times g of x. Our goal is to get this equal to a times t on f of x plus b times t on g of x. If we can show that that is true, right, that's what we want to show. If we can show that that is true, then we have a linear transformation. If we cannot show that that is true, then we might not. And in fact, we might be able to show that it's false. But we don't have a lot to go on here. All we have is the definition of this transformation. We evaluate a times f of x plus b times g of x when x is 1. And we evaluate a times f of x plus b times g of x when x is 2. And we make that the components of our vector in R2. Now, because this is in R2, I can use the properties of vectors to rearrange it. I'm adding stuff in each of the components. So I can think of that as adding two vectors together. I am multiplying each of the components in the first vector here by a. So I can think of that as multiplying a times the vector f of 1, f of 2. I am multiplying b times all the components in the second vector. So I can think of that as b times the vector g of 1, g of 2. And with that, we've basically got it, because f of 1, f of 2 is exactly the transformation on f of x, and g of 1, g of 2 is exactly the transformation on g of x. We have shown the thing we said we were going to show. That's what it takes to prove that this transformation actually is linear. Now that we know that, we can start investigating a little bit more closely. We said that if a transformation is linear, then it can be determined entirely by its action on a basis. So let's keep looking at t evaluated on f of x is equal to f of 1, f of 2, and recall that the standard basis for P3 is the polynomials 1x, x squared, and x cubed. Pretty quickly, I can evaluate t of 1 is going to be 1, 1. T of x. Well, when x is 1, x is 1. And when x is 2, x is 2. That's strange to say, but it works. T evaluated on x squared. 1 squared is 1, 2 squared is 4. And t evaluated on x cubed. 1 cubed is still 1, 2 cubed is 8. So with that, we have two options on how to evaluate this particular linear transformation. If I want to evaluate t on, say, 3x cubed plus 5x squared minus 2x plus 9. Well, I can do the direct evaluation because I know it for this particular problem. That is 3 times 1 cubed plus 5 times 1 squared minus 2 times 1 plus 9, and 3 times 2 cubed plus 5 times 2 squared minus 2 times 2 plus 9. And I can throw that into a calculator. 3 and 5 is 8, minus 2 is 6, plus 9 is 15. 3 times 8 is 24, 5 times 4 is 20, 2 times 2 is 4. So we have 24 plus 20, which is 44, minus 4, which is 40, plus 9, which is 49. Or if all I had to work with was the action on the basis, this is going to be 3 times the transformation on x squared, which is 1/8, plus 5 times the transformation on x squared, which is 1/4, minus 2 times the transformation on x, which is 1/2, plus 9 times the transformation on 1, which is 1/1. And then you see that the calculations actually end up about the same. We've got 3 plus 5 minus 2 plus 9, which is still 15. We've got 24 plus 20 minus 4 plus 9, which is still 49. You get the same thing either way you approach this particular linear transformation. Great. Once again, I'm going through things fairly quickly because these are mostly ideas we've seen before, just a little bit weird seeing a transformation on two vector spaces of such different character. And as we move ahead, we spent a lot of time talking about the vocabulary on matrix transformations, transformations on Euclidean vectors. And I want to use exactly the same vocabulary here. Let's consider a linear transformation T . Then the kernel of T is denoted and defined. The set of all vectors little v in vector space V, such that T of little v is the zero vector. Again, we've talked about kernel before, slightly different context here, but the same idea still holds. The range of T is the set of all T of V, such that V is a vector in vector space V. And like I said, we've talked about the kernel and the range of a transformation before. We said it specifically in terms of Euclidean vector spaces. It extends exactly into generalized vector spaces. The kernel of T is a subspace of V, and the range of T is a subspace of W. Those are a couple of interesting properties. I encourage you to spend some time playing around with those on your own. But for the sake of time, I'm not going to get into them in this video. And from these, we can describe the rank of the transformation as the dimension of the range. We can describe the nullity as the dimension of the kernel. And if you add the rank and the nullity, you get the dimension of your vector space V that you started with. All stuff we talked about with Euclidean transformations still holds true for generalized transformations. Not too exciting. I don't want to spend a ton of time on that, but mentioning all of that I think is worthwhile. Let's yet again let T be a linear transformation from vector space V to vector space W. I'm using the wrong variables here. Sorry about that. We say that T is a one-to-one linear transformation if and only if T of V1 is equal to T of V2, only when V1 and V2 are equal. Of course, when V1 and V2 are equal, then it has to be the case that T of V1 is equal to T of V2 by simple substitution. When there is no other possibility, then we get this idea of one-to-one. We say that T is onto if and only if the range of T is in fact W. Another way of thinking about that, for all vectors little w in vector space W, there exists a vector V in vector space V such that T of V is equal to W. The reason we care about one-to-one and onto is that whenever a transformation, whenever any function is one-to-one and onto, then there exists an inverse. I should use my words. So if t is both 1-to-1 and onto, then there is an inverse function, which we write t superscript -1, which is going to go from w to v and have the property that t of t inverse of w is equal to w for any vector w in vector space w, and t inverse of t of v is equal to v for all vectors v in vector space v. You have dealt with inverse functions before. There's really nothing new going on here. As far as that goes. The one thing that is going to be new, if you have a 1-to-1 and onto linear transformation, then not only is the inverse going to exist, but T inverse is also going to be a 1-to-1 and onto linear transformation. And that's the thing that is so valuable to us. So proving that one piece at a time. 1-to-1. Remember that to show that a transformation is 1-to-1, we want to let W1 and W2 be in vector space W such that T inverse of W1 is equal to T inverse of W2. And we want to show that this can only happen if W1 and W2 happen to be equal to each other. Well, I can pick a vector v such that v is equal to the T inverse of W1. And then, by the definition of the inverse function, that means that W1 is simply T of v. But since T inverse of W1 is equal to T inverse of W2, that means that it is also the case that V is equal to T inverse of W2. And by the property of inverse functions, that means that W2 is also T of V. If W1 is equal to T of V and W2 is equal to T of V, by the transitive property of equality, it must be the case that W1 is equal to W2. So using the definition of an inverse function and using the transitive property of equality. Next, we want to show that T inverse is onto. So remember, T inverse maps from W to V. And to show something is onto, you want to pick an element of the codomain and show that there is an element in the domain that gets there. Well, I can use the original function t to take vector v and turn it into vector w, something in the domain of t inverse. And by the definition of an inverse function, this means that v is equal to t inverse of w. And that's really all it takes to show that a function is onto. Last but certainly not least, we want to show that t inverse is linear. And we're going to start off kind of similar to what we did to show onto. If we have two vectors in W, well, since t itself was one-to-one and onto, then there are two vectors, v1 and v2, in vector space V, so that t of v1 is equal to w1 and t of v2 is equal to w2. And then the last thing we need is two real numbers. And to show that a function is linear, we want to take the inverse of the linear combination, c1w1 plus c2w2. And if this is linear, then this is going to be equal to c1 times t inverse of w1 plus c2 times t inverse of w2. That's what we want to show here. So we have to figure out a way to do that. And I've kind of hinted as to how we're going to do that with how I set everything up here. We know what W1 and W2 are in terms of V1 and V2. And now, if we look inside these parentheses and just focus on this bit right here, that is a linear combination of stuff involving a linear transformation. And normally we do this in the other direction, but there's no reason we can't take that linear transformation and rewrite it as t of c1v1 plus c2v2. Right? That's what it means to be a linear transformation, just written backwards of how we normally do it. And now what do we have? We have the inverse transform of the transform of this linear combination. Definition of inverse functions tells us that the function and its inverse cancel each other out, leaving you with the linear transformation we care about. Now, one last step. If t of v1 is equal to w1, then by the definition of an inverse function, v1 itself is T inverse of W1. And V2 itself is T inverse of W2. That gives us the linear combination we were after. That shows that this is, in fact, a linear transformation. All right, a lot of vocabulary there, a little bit of proof. Hopefully nothing all of that outlandish. I'm going to wrap up our discussion here. Certainly there are a number of problems in the practice set that ask you to find the inverse of a transformation and play around with just that basic principle. But finding inverses of functions, I hope, is something that you're familiar with from previous algebra coursework. In the next video, we're going to look at a different thing that we can do with a one-to-one and onto function, not necessarily worrying about this inverse thing. But I'll let that talk about itself in the next video. Wrap up here and see you then.